So yesterday we started off with the simplification techniques. There are two kinds of simplification technique. One is an algebraic method and other is called as a K-maps or Karnaugh maps. Now, what is algebraic simplification? This algebraic simplification will use theorems and postulates. And if you want to perform this, you must have knowledge about what are the different postulates available for Boolean algebra, and then what are the simplification methods that are available. So which means you require some kind of a skill set to perform this algebraic simplification. Whereas in case of K-maps, you do not require any background on the theorems or postulates. This K-map is a diagrammatic technique, which means that we will be using some kind of a table and then we will be trying to use some common elements. So it is, as humans, it is really very simple. For computers to perform, algebraic simplification is better when compared to the K-map techniques. First, let us explore the algebraic simplification. Let us find out the difficulty that we will face as humans in algebraic simplification. Then we will take up the K-maps. Now, when you consider the algebraic simplification, all you need to know is how many literals are available. And before that, what is your main objective in the complete simplification technique? The main objective in the complete simplification technique is to reduce the number of literals. Right? You must reduce as much literals as possible. Only then your design will be approved. Again, if say for example, two students are, I gave you an example in the last class itself, that if two students are coming up with an expression, one might have an expression of 5 variables, but other might have an expression of 3 variables only. And with the minimum number of gates, only the one who is producing the output with just minimal number of gates will be considered as a simpler design. Okay, so always your objective must be to use as many less number of gates as possible. Now let's take up an example for an algebraic simplification. Let's take this example here. X plus y multiplied by x plus y bar multiplied by x bar plus z. You have to simplify this. Obviously, how many variables you have? You have 3 different variables, right? What are the 3 different variables? X is one variable, y is one variable, and z is one variable. And their complements will include x bar, y bar, and z bar. These are their complements. So which means taking together the variables and their complements, we have now total 6 literals we have. Please do not say that we are having only z and z bar is not available. During the simplification process, you might have to include z bar at times. Then you will have, instead of z, you might have z bar. Similarly for the other variables also. So now let us work on how to simplify this. So what is the normal procedure we will follow to simplify? We will first multiply all the variables straightforward directly, right? So this is a very, very simple Boolean expression. So that is why it has been taken, but still as humans, we will face some kind of a difficulty here. So how do we simplify? We will just apply associative property here. X multiplied by x, x multiplied by y bar. So x dot x and x dot y bar. Y dot x and y dot y bar. Y dot x and y dot y bar here multiplied by x bar plus z. And further let us multiply this x bar plus z using associative property inside. So we know that x dot x is nothing but x only. And that multiplied by x bar, what is 1 dot 0? 1 dot 0 will always be 0. So x dot x bar will always be 0. Hence this is 0. Similarly, x dot y bar dot x bar, this will also be 0, right? This particular term, because x dot x bar you are having. And then let us multiply this x dot z is this z multiplied by this term. So x dot y bar multiplied by z, then y dot x multiplied by x bar will be 0, right? So this will be 0. Y dot x multiplied by z.
నేను రాలేనమ్మా నువ్వు వెళ్ళా నాది అవ్వలే నేను పంపించలేదు నేను దానికి పెట్టించుకుంటే పెట్టాల్సిన
Ajita, खाना खा लिया? Nice music, right? Ajita, could you mute yourself? Ajita, please mute. Yeah. Okay. So let us apply the associative property. So similarly, y dot y bar is already 0, right? So this multiplied by anything will be 0. Hence, I have written just plus 0. Now, let me just erase this part here. Yeah. Now, if you see, what are the leftover min terms here? X dot z, right? X dot z, and x dot y bar z, and x y dot z. So, Ajita, please mute, or I think I will mute. Oh, she is muted. Okay, good. So here, if you take x dot z, and if you compare these three terms, this particular term and this particular term, min terms, they have x dot z as common. So x dot z multiplied by, so 1 plus z will be there, and plus this particular term. 1 plus anything is 1 only, right? So this vanishes. So you will have x dot z. Again, in this also, x dot z is common. So you take x dot z, it will be 1 plus y bar, 1 plus y, anything is 1 only. So you have x dot z. So if you look, this whole term has been simplified to just one min term consisting of two literals, x dot z. And if you look at the effort that we have taken, we have applied associative property. We might go wrong in identifying some similar expressions. We might have to consider this x dot x bar as 0. At times you will have two terms, say here x z also you might have one more x z here. You will have to identify all those things. You have to find common terms among two min terms, and then pull them everything to common. So you might go wrong, right? So this is the difficulty. So you require a lot of algebraic manipulation while performing this algebraic simplification. But one advantage that we have is you can apply you have your complete freedom to do any method that you want. Here we have applied associative property. If you find that simplification using distributive property or even De Morgan's theorem, if it can simplify, then you are free to do, right? So that little freedom we have, and the advantage as listed here, it is an open-ended and form as desired by the user. They can simplify on their own, right? Now let's take another example, very practical example, a half-adder circuit. Though you have heard this particular term in our labs, half-adder. What is this particular half-adder? Half-adder is a circuit that will add two single bits, and it will produce two outputs, sum and carry. So the general block diagram of a half adder is given like this. So you will have a digital circuit here. You have two inputs. All these X is a single bit input. All these are single bit inputs. X and Y are two single bit inputs. What do you mean by single bit input? Say for example, I am adding 0 and 0. What will be the output? My sum will be 0 and I will not have carry, right? I don't have any carry here. Similarly, if I add 0 and 1, if I add, sum will be 1 and I will not have any carry, right? I will not have any carry. So this is a carry term and a sum term. Similarly, if I add 1 and 0, 1 plus 0 was 1 and I don't have a carry here again. So carry is there and sum is also there. Finally, if I add 1 and 1 here, 1 plus 1 is 2. So which means the binary is 0, 1. So here sum term is 0 and carry term is 1. So that is the reason we have two inputs here, two single bit input and two output. One is called as a sum and other is a carry. If you create a truth table for the input and output combinations, so your truth table will be like this, right? So maybe let me draw the truth table for your convenience, right? So here, what are the input variables? X is one input variable, Y is one input variable. Sorry, sum is one input variable and carry is one input variable. Now the input possible combinations are 0, 0, 0, 1, 1, 0 and 1, 1. So when you add 0 plus 0, what was the sum part and carry part? You look here, sum part is 0, carry part is also 0. So sum part is 0 and carry part is 0. When you add 0 and 1, when you add 0 and 1, sum part is 1, carry part is 0. Sum part is 1, carry part is 0. Similarly, 1 plus 0, sum will be 1, carry will be 0. When x 1 and 1, your sum part will be 0 and carry part will be 1. Now, how do you simplify this? How do you simplify this? Now, if you look at this particular table, what is the expression for sum? This is what you need to find out. And looking at this particular column, your sum, where do you have ones? Your sum ones are here. And what is this particular one corresponds to? This one corresponds to an input of 0 and 1. 0 means it is x bar and 1 means it is y, right? So this particular 1 corresponds to 0, 1 corresponding to x bar y. And there are two outputs, right? So sum, this or this are the outputs here. So we use OR expression here. And what is the Boolean min term corresponding to this particular one? It is x is 1 and y is y bar, which means it is x y bar. This is how we write the Boolean expressions. Similarly, for carry, if you look, where do you have the one along looking at this particular column? Your carry 1 is here. Your carry 1 is here. And this one, the input combination corresponds to 1 and 1, which means that carry can be given as x dot y. X dot y. So these are the two expressions. Now, if you implement this particular expression using the logic gates, AOI gates, so what are the inputs we have? We have two inputs, x and y, right? So I'm going to implement using logic gates here. So first is x bar. So this is x bar and y, x bar y. So they are ANDed together. And then you have x here and y bar here. This is x y bar, this is x bar y, and they need to be ORed together, right? So they need to be ORed together. So this will be the sum expression. Now, what is a carry expression? Carry expression is just x dot y. So, where is x? I'm having x here. I think it is y. I forgot NOT gate here. So you will have y bar. Yeah. So now what is the carry term? My carry term is just x dot y. So this is my x. Okay, let me use different color. So this is my x and this is my y. Right? And of this will be my carry expression. So this will be my sum expression. This will be my carry expression. So this is how a digital circuit is implemented. Now, if you look at the whole circuit, I can represent this as this complete thing as a block. This complete thing as a block. So this is my half adder circuit. And what are the inputs I am having? The inputs I am having are two inputs, X and Y are the two inputs. And what are the outputs I'm having? I'm having sum and carry as my output. And inside this black box, I'm having the circuit that I have done here. Right. So this is how we represent a half adder circuit. Now, in other terms, instead of having this complicated circuit, what is the complicated circuit that we are having here? Look at this combination. A NOT gate, an AND gate, a NOT gate, and an AND gate, and an OR gate, right? But we have already seen somewhere that this particular expression here, x bar dot y, this expression you must have seen somewhere that this expression is equivalent to x XOR y. This is equivalent to x XOR y. So in a simpler form, the complete circuit can be redrawn as I'm having an x term, I'm having an y term, right? This is nothing but an XOR of XOR x XOR y is our sum term, and the AND operation of this is our carry term, which is nothing but x dot y. So simply what we can do is, this is our black box, right? So this is how we implement our sum terms and carry terms. Any doubt here? Now let's look at the other method of simplification. Yeah, please.
Sir, do we only
Yeah,
have
please go ahead.
represent one? Like, sir, for the sum term, why did we not represent it as x plus y?
X plus y, in Boolean algebra, x plus y will get you an OR operation. It will get you an OR operation, right? So just check whether does your sum column satisfies this OR operation x plus y. 0 or 1 is 1, 1 or 0 is 1, 1 or 1, this will also will be 1 if you are using x plus y. Am I right? So we have to satisfy this particular column. And how this is, so that is the reason, first thing what we did was, we wrote a Boolean expression, and that expression, luckily, this is equivalent to a single gate, which is an XOR gate. So we used this XOR gate. Have I clarified?
Yes, sir. I was just checking for two of the values, second and third.
Now, third one is, you have to check all input combinations. Okay. Now, let's move on to the K-maps. As I've already said, K-map is nothing but a graphical technique to simplify the expression. Please note that the very, very important point here is these K-maps are useful only till 6 variables only. What will happen when you go beyond 6 variables is, as human beings, we cannot visualize how they are going to map. So that is the reason when K-map fails, then we move on to another method, which is called as a tabular method. a tabular method of simplification, whenever K-map fails, we use this tabular method. Tabular method is a slightly lengthier method, and at the same time, it is very effective when your variables are large. If you have 6 variables, just imagine you have variables say A, B, C, D, and then E and F. It is easy only if you go in for a tabular method when your variables are more than 6. Even if your variables are 6 also, you can go in for a tabular method. If your variables are more than that, say G and H, then definitely tabular method is important. You will realize that as variables increases, how your table gets multiplied. So we will see that now. Now, what is the step? What is the step is any expression that you have, a given Boolean expression, first convert it into a canonical form or a standard form, right? So the first thing that you must do is reduce the expression to a canonical form, right? And then try to get the minimum number of product terms if possible. And each product must have a minimum number of literals also. Now, you must always make sure that the expression that you are minimizing gets implemented in a 2-level implementation. What do you mean by a 2-level implementation is, say you are giving some inputs, right? These inputs are processed with different gates. It can be a multiple combinations. So here also in this particular circuit, in this circuit, if you see, this is a 2-level circuit. What is a 2-level circuit here is, let me highlight using this yellow. This particular part, forget about these X bars, right? Just look at this gate here, and this gate here. This gate is receiving its input directly, right? I said forget about X bar in the sense at times you can have X bar as a direct input, low level input you can have. So that is the reason we are ignoring this NOT gates. So this is level 1. The first gates that your inputs are getting processed is level 1. And what is level 2 implementation is all these combinations are getting processed here, right, across this OR gate. So this is your level 2 gate. So most digital circuits get implemented using these 2-level logic. If you are using an SOP expression, please note that if you are using an SOP expression, sum of products term expression, or even POS expressions, they automatically get simplified using a 2-level implementation. So this is the first level, all these are first levels, and this is the second level, right? You will understand as we build upon different circuits. Now, how do you visualize this K-map? You can visualize this K-map as a simple Venn diagram. What is a Venn diagram? If you recall, if you consider that this is a single set, right? We are having a single set here, and if there are 2 variables here, let us assume that there is a variable A, right, and another variable here which is a variable B, and another variable here. So let us assume that this is variable B. Please note this is variable B and this is variable A, right? Now, what is it possible I can fill color? No, I can't fill color, right? Yeah, let me highlight. Now, what is this particular section corresponds to? This particular section corresponds to A. This is the larger portion is A with B removed, right? Only this particular part with B removed. So I can write it as A B bar, right? Negated value of B. Similarly, what is this particular portion? I've just highlighted here. This particular portion is, this portion corresponds to B with a complemented A. So A bar B I can write. Now what about this portion, this combined portion? This combined portion is nothing but both A and B are there, right? Sorry, I think it's A bar and B bar. No, A and B, right? Sorry, both A and B are there. So this is A and B. What about this region? Some other color. What about this regions? In this region, you don't have either A, so A bar, and you don't have either B also. So this region is called as, corresponds to A bar, B bar. So we are, for two variables, the sets that we are having are AB, A bar B, AB bar, and A bar B bar. These are the sets that we are having here. Now, each set, a combination of each set can be simplified into a simple expression. What is that? If you add these two expressions, say for example, this one, this circle completely, this is nothing but sum of what? Sum of A B bar plus the intersection part, which is AB, right? This can be how you can simplify this. You pull out A from this because A is common in both these expressions. You have B bar plus B. What is B bar plus B? It is nothing but A dot 1, which is equal to A. So we have got the A circle here. Similarly, you get the B circle. This B circle here corresponds to what? This corresponds to A bar B plus AB. So B is common in both the cases. So we have A plus A bar. A plus A bar is 1. So this is equal to B. So we have got the B circle here, right? So we have got the B circle. So likewise, if you want to add both the expressions or these three expressions, what are the three expressions we have? Let me write here. I'm going to add the three part here. So we have A B bar as this particular circle, the intersection part, which is AB, and A bar B. This must be equivalent to what? This must be equivalent to both the circles A and B circle, right? So let us try to simplify, and we will see that they will be equal to AB. And how do you simplify? As I said, you require some kind of algebraic skills here. So here, AB bar, this AB can be written one more time because that does not alter the expression at all, right? AB plus A bar B, right? If I write 1 and 1 plus 1, it doesn't change. 1 or 1, it doesn't change, right? So you combine this particular part, which is what we have done here. So you got A. You combine this particular part, which is what we have done here, which is A plus B. So we have got a combination of A and B circles. So you can visualize a two variable map as a Venn diagram map. Okay, but K-map, on the other hand, it doesn't look like a Venn diagram, but these are matrix of squares. These are matrix of squares in the sense, and let me draw now a K-map now. I'm going to draw a K-map for two variables. Please note that we are going to operate for two variables. And what are the variables we are going to operate? We are going to operate for X and Y. X and Y. So how does the K-map will look like is, K-map will look like a matrix of squares. It will look like a matrix of squares, and for a two variable input, right? So how many input combinations are possible? What is 2 power 2? 2 power 2 is 4, which means that 4 input variables are possible. So this matrix square will be divided into 4 different squares. Now this has been divided into 4 different squares. And each square here will represent a minterm. So as mentioned here, each square will represent a minterm, and the other rule is each adjacent square will differ only by one literal only. Why we should do that? Why we should do that is because we are going to apply this particular rule, a plus a bar will be 1, so that you can simplify. Okay, so again, we are going to do a 2 variable map. As I have already said, the 2 variables means number of input combinations are 2 power 2 4. Now how do you do? Always for this x and y variable, we will divide it like this. Maybe x for column wise and y for the row wise, or the other terms, y for row wise and x for the, I'm sorry, yeah, y for the column wise and x for the row wise, which means that x and y, what are the possible input combinations? X can take 0 and 1, right? So here this row corresponds to x equal to 0 and this row corresponds to x equal to 1. Similarly, this column y will correspond to, what are the input possible combinations of our y? The input possible combinations are again 0 and 1. So this column corresponds to 0 and this column corresponds to y equal to 1. Whenever we say x equal to 0, it means that this corresponds to x bar and this row corresponds to x. Similarly, whenever we say that y equal to 0, this column corresponds to y bar and this column corresponds to y. Now, I've already said that each square corresponds to a minterm. What does this mean is, so this square is an intersection of x equal to 0 and y equal to 0, which means that this matrix corresponds to a value or a minterm x bar y bar. Similarly, this matrix corresponds to x bar y. This matrix corresponds to x y bar and this matrix cell corresponds to xy. Now, what is the decimal equivalent of x bar y bar? X bar y bar is 0. So, which means that this cell corresponds to a minterm of m0. This cell, the second cell, corresponds to x bar y. What is x bar y? It is 0, 1. 0, 1 means it is 1. So, this cell corresponds to a minterm of m1. And similarly, this cell corresponds to a minterm of m2 because it is 1, 0 and 1, 1 a minterm of m3. Right? So, this is how your K map will look like. So, yeah. Any doubts till this? Okay.
Excuse me, sir.
Yeah, please.
Sir, in the part that you were teaching through the Venn diagram,
Yeah.
where we went to A plus B, so in that, wouldn't the AB part be counted twice that way?
Please note that this is, we are studying logical circuits. Whenever we say logical circuits, it is very much different from our algebra. Algebra in the sense our mathematical normal algebra. But here we are looking at Boolean algebra here. That's what I said. If I write as, say, A plus A, this is an OR operation of A and A. So OR operation of A and A will always be 1. If I write, sorry, it is not 1, it is actually A, right? So that is the reason we write if AB, if we are having a minterm here, there is no harm in writing one more AB because they are logical OR operation only, their resultant is still AB only. So that is the reason we have just added one more AB and then we did the algebraic simplification. So that is why I said algebraic simplification requires some kind of a skill set, right? So you will, yeah. So have I made it clear? Why did we add AB twice?
Yes, sir. Thanks a lot.
This is a logical OR operation. It is not the physical sum actually. Okay. All right. So now let's take an example of a half adder. You might recall that your half adder circuit, where did I, yeah, this is the truth table we had, right? Is it okay? I am copy this. Let me try if I can copy. Good, I've copied. Okay, so maybe I will erase the unnecessary parts. I don't want this, I don't want this. Yeah, okay. Okay, so this is the 1010. Yeah, this is the truth table for a half adder, right? Now, how do we draw the K map for this? For every output column, we must create so many number of K maps, meaning, so this is the K map that I'm going to draw for sum. This is a K map I'm going to draw for sum. Okay. Now, similarly, I will make one more K map. I will make one more K map for carry. Okay. So since I am going to work for sum, there are 4 input combinations, right? So, and it is a 2 variable K map. So I will be having 4 cells, 4 matrix cells, one for X and other for Y. So this corresponds to Y bar and this corresponds to Y. This row corresponds to X bar and this row corresponds to X. So this cell corresponds to a main term of M0. This cell corresponds to M1, M2 and M3. These are the cells corresponding to sum. Similarly, I will do it for the carry part also. Again, for carry part, what are the input combinations? This carry column, there are the input combinations are again X bar and X, Y bar and Y. Please note that there is no hard and fast rule that your X must be row wise and column must be Y must be column wise. You can also have this way also, that is Y and X here. In that particular case, what is the only difference is this min term will be here, M0 will be here, M1 will be here, M2 will be here and M3 will be here, and it doesn't matter, both are same. Okay, now we have created the K maps now. Now we have to make entries. So what are the entries? Please note 0, 0 corresponds to 0, right? With in this particular cell, I am writing only for sum only. So 0, 0 corresponds to the min term M0. So it is 0 here. And 0, 1 corresponds to 1, which is 0, 1. X is 0 and Y is 1. So M1. So this corresponds to 1. 1, 0 corresponds to 1, 0. Where is 1, 0 cell? 1 and 0 cell. So this will be 1. And 1, 1 corresponding to this. Okay. Now similarly for the carry part. For the carry part, everything M0 is 0, M1 is 0, M2 is 0, and M3 is 1 here. So this is how we make the entry here. Okay. Now, how do you write the Boolean expression here? Again, we write the Boolean expression as, say, sum is equal to this particular K map corresponding to sum equal to this one corresponds to which cell? This one corresponds to X bar Y cell plus this cell corresponds to X Y bar. Similarly, carry corresponds to which cell? It corresponds to X Y. It corresponds to X Y. So this is how we get the Boolean expressions. Any doubt? We have taken a very, very simple problem for a half adder. Okay. Yeah. Now let us do a 3 variable map. And how do we do a 3 variable map is, again, the first step is okay. Now the variables are 3, right? So there are 3 variables here. So what are the 3 variables? The 3 variables are X, Y, Z. If there are 3 variables, how many input combinations are possible? 2 power 3 input combinations are possible, which means that there will be 8 cells. There will be 8 cells. So how do we create 8 cells? How do we create 8 cells is, we can have 8 cells either like this, or another method is also there. You can have, or you can also have cells like this. So what are the variables here? What are the input possible combinations? What are the input combinations? You have the three variables are x bar, y bar, z bar, likewise, right? So you can either group x and y together, either you can group x and y together, and z can be row wise and xy can be column wise, or you can choose y and z together so that y and z will be column wise and x can be row wise. Any way is possible. So either you can split x on one side and yz on other side, or you can split xy on one side and z on other side. Okay, so it is always suggested that if your variable sequence is xyz, it is always suggested that you combine the variable such that in a sequence only. Don't combine x and z, don't combine x and z and then y in a separate column or row, right? So this will create a lot of confusion. You will have to, it is not difficult, but it will create confusion. So that is why it is suggested that it is avoidable. You should avoid creating such kind of combinations. Instead, as they are in the sequence, either you combine this xy or you combine this yz, which are in sequence. So that will be better for us to visualize things. So if it is x, then along the row wise, this will be x bar and this will be x. Okay. Now coming to column wise. How many columns will be there? Since there are two variables, there are 4 different columns will be there. Please look here very carefully. There are 2 variables on the column wise, right? So when I have 2 variables y and z, what are the input combinations in sequence? 0, 0, 0, 1, 1, 0 and 1, 1, right? So these are the input combinations possible. So the first cell, first column will have an entry 0, 0 corresponding to y bar, z bar. Now please note that there was one rule just we studied, that each adjacent cell here, each adjacent cell must differ by only one literal only, which means that you must apply the gray rule. What is the gray rule? That is, the next sequence must change only by one variable only or one literal only. So meaning here if it is y bar, z bar, next variable must change, either y bar must change or z bar must change. In the sequence, what is that you have? You have y bar, z. So the gray cell change sequence is accepted. But after this, if you see, if you follow the same sequence here y bar is also changing and z is also changing. So y bar is changing from y, z is changing from z bar. So you should not follow this order. So what each adjacent cell must change only by one literal. So instead of this, you must change, let us keep z as it is, let y bar gets changed to y, z, and then in the next column, one of the variable again must change. So there you can have y and let z bar can change. So following this sequence, I am going to write the sequence here. Next 0, 0, 0, 1, which means that this column corresponds to y bar z. And the next column will corresponds to y, z, and this column corresponds to y, z bar. Please note that there is a grayscale change between the adjacent cells, meaning this cell corresponds to, the first cell corresponds to a min term of m0, right? This cell corresponds to 0, 0, 1, so m1. This cell corresponds to 0, 1, 1, m3. This cell corresponds to 0, 1, 0, M2, and this cell corresponds to 1, 0, 0, which is M4. This particular cell corresponds to 1, 0, 1, which is M5. This cell corresponds to 1, 1, 1, corresponding to M7, and this cell corresponds to M6. Why? Because it is 1, 0, 1. Any doubt here? Likewise, let me fill up this the next table also, where we have XY sequences combined. So you will have 4 rows now. Here you will have 4 rows. There will be no confusion along the columns because we are having only one variable. The first one corresponds to Z bar and the next one corresponds to Z. Here the first row corresponds to 0, 0, X bar, Y bar. Next one corresponds to X bar, Y, 0, 1. This corresponds to X, Y because only this particular variable has changed. And next row corresponds to X, Y bar because this grayscale change will happen here. Here again you can see only Y bar has changed. Right? So that is what we want. And what is the minterm corresponding to this particular cell? This cell corresponds to 0, 0, 0, M0. This cell corresponds to 0, 1, 0. So it is it right? Yeah, M2. This cell corresponds to 0, 0, 1, M1. This cell corresponds to 0, 1, 1, M3. This cell corresponds to 1, 1, 0, which is M6. This cell corresponds to M7. Here, this one corresponds to 1, 1, 0, which is, 1, 0, 0, which is M4. And this corresponds to, there's a bar here. 1, 0, 1, which is M5. Now look at the sequence here. It is M0, M1, M2 and M3. Let me jump. M0, M1, M2 and M3. And then M4, M5, M6 and M7. Here M0, M1, M2, M3. From M3, M4, M5, M6, M7. Okay. Any doubt here in making the K-maps? Yeah, that's what I said. I've already explained all these particular parts, but still, so there will be a grayscale change as mentioned here. 0, 1 will change to 1, 1 only because only one literal needs to be changed. Now, in this layout, if you see, any two adjacent minterms will definitely have one common term. In the sense here it is Y bar, Z bar. Here also you will have Y bar, right? So here between these two, what is the common term you are having? In between these two, Y bar is a common term you are having. Between these two cells, Z is a common term you are having. Between these two cells, Y is the common term you are having. And between these two, there will be no common terms. But one thing that you must see here is this can be, this column, this first column and the last column can be wrapped. Wrapped in the sense, you can always compare, you can always say that this column is adjacent to the first column. If you wrap, if you consider that this is the edge of a paper line, this edge of a paper line and this edge of a paper line can be pasted together. If that is the case, what is common between this column and this column? It is Z bar is common between the first column and last column, right? So this you must remember. So that's what I said. You can always wrap around the sides of the K-map. So wrapping around, why are we doing this adjacent, this grayscale sequence here is because that will simplify our K-map very easily. Say for example, if you have, let us take these two cells, this cell corresponds to X bar, Y bar, Z bar. This cell corresponds to X bar, Y bar, Z. You take, this is minterm M0 and M1. You take X bar, Y bar common, you will have Z bar plus Z. So Z bar plus Z is nothing but 1. So these two can be combined and just return as x bar, y bar. So that is the advantage we will get when we are using this grayscale. So as I mentioned, you can wrap around the sides of K-map. In terms of first column and fourth column, they are considered to be next to each other. So just as an example, if you take, let us take this M6 and M4. What is M6? M6 is nothing but X, Y, Z bar plus X, Y bar, Z bar. So what is common? X, Z bar is common here. Y plus Y bar. So this can be simplified as X, Z bar. Okay, right. Yeah. And few more things. Each cell in a 3 variable K-map, they are adjacent neighbors. Always never look at the diagonal elements. Either look at the rows or columns. Diagonal elements you should not always look at. In general, each cell in an n variable K-map has n adjacent neighbors, right? So if you consider what are the neighbors here, let me erase this. If you consider what are the neighbors of this particular cell, the neighbors of this particular cell are this one, this cell, and this particular cell. You should not look at the diagonals. You should not look at diagonals. Okay. Now I think we will wind up here, and then we will look at more examples as we move from 3 variable to 4 variable map. Any doubt here? Any doubts?